Welcome to Chemistry 111 on this lovely Friday. We are going to start by finishing reviewing for the test, which we're going to have not this weekend, but next weekend. So they'll probably be sent out midweek, Monday at the earliest, Wednesday probably at the latest, but with a due date coming that Sunday. So a week from this Sunday. That's pulling up the test. Where we left off, we had just briefly talked about lattice energy. Number 5, lattice energy. We discussed that in order to do a problem like this, first you need to look at the expected charges of both cation and anion. The larger the charge on both, the larger the lattice energy. If two ionic compounds had the same charges, then you must look at the size. The bigger the atom, the lower the lattice energy. And so what we found out was MgO is the highest, followed by NaO, followed by NaF, followed by NaI. So answer D was the one that places them in order of increasing lattice energy. We don't have to worry about number 6, but we can work on number 7 because it's the electron configuration one. What is the most stable ion of an atom with a neutral electron configuration of 1s2, 2s2, 2p4? So the key thing here, remember, the most stable state we can achieve is a completely filled orbital. So 2p4 puts us at oxygen. And so to get to 2p6, which would be neon, it would typically be 2 minus. And so the answer would be B, 2 minus. We're not going to do a whole lot of these problems. Let's see, number 9. Place these isoelectronic series in order of decreasing size. Decreasing size. So not increasing, but decreasing. But the rule for isoelectronic is simply this. We have the same number of electrons, different number of protons. And that means that the more protons you have, the more positive charge you have, the more the protons can pull the electron cloud in, the smaller it is. So we want the most positive atom to be the smallest, the most negative atom to be the biggest. So all things considered, you would want strontium 2+ to be the smallest and selenide 2- to be the biggest. So the only one that matches that would be A. A has selenide, then bromide, then rubidium, then strontium. But be prepared to do questions like that. Label them as largest, second largest, smallest, and second smallest. We're skipping a bunch of the stuff. A lot of this is chapter 6 and chapter 7. We will get to this a little bit later. We don't know how to do this right now. Chapter 5 didn't play a super huge part in this test, but it played enough of one. Which of these elements would have the lowest electron affinity? So this one is a little hard, and this is actually probably a bad question. I would probably accept 2 answers with a good argument. As I said, I'm not going to try to throw in exceptions to the rule. The generalized trend says that the top right elements would have the highest electron affinity, meaning they would get the most energy from gaining electrons. And the bottom left elements would get the least energy from gaining electrons. If you just went on that alone, it becomes between rubidium and manganese. Rubidium and manganese. Well, rubidium is the furthest bottom, but there is a weird exception with magnesium that maybe because magnesium is in the 1s2, it would not actually want to gain an electron, less so than rubidium. And without actual numbers, you could maybe argue magnesium fits an exception, and so it becomes the lowest electron affinity. But if you were just arguing based on the trend alone, rubidium would be the correct answer. So that one was a bad question, so we'll deal with that. But that was all the chapter 5 questions we could have on the test. Electron affinity. I included a bunch of stuff on this, including atomic radii and electronegativity values, and that's not something we're going to necessarily use. Okay. Closing that out. And now we'll start looking at chapter 6, which is covalent bonding. So, any second now. There we go. Last chapter, we finished talking about the chapter by talking about ionic bonding, where essentially electrons are transferred from one atom to the other to give them noble gas electron configurations. Sodium had lost its one electron from the 3s row and thus became like neon with a 2s2, 2p6. Chlorine had gained one electron to be like argon, being 3s2, 3p6. So sodium chloride saw the transfer. Well, what we're going to also learn is covalent bonds. Covalent bonds, instead of transferring electrons, we're going to share electrons together to make the same noble gas electron configuration. It's going to allow these electrons to be counted for both the atom they belong to and the atom they share with. So having one electron is not a bad thing if you can share it with a guy who has another one electron to give you two. But it gives the other guy two as well. And the general premise here is, oh shoot, is that the Lewis theory teaches us that the atoms will gain, lose, and share electrons until they get that noble gas electron configuration. We're not going to go any higher than the noble gas because of the energy difference between the current principal shell and the next energy shell. Go promoting from 2s or 2p to 3s, too much energy. So we don't want to add any more than the noble gas. Now this phenomenon we're going to call the octet rule, named after the fact that there's 2s and 6p electrons that can be held, thus making that 8. We're going to try to achieve 8 electrons or an octet around just about every atom. There's only one real exception, and that is hydrogen. Hydrogen can only have 2 because it only has the 1s orbital. So that's only going to ever need 2 electrons. But other than that, every other atom can hold at least 8. And we're going to strive for 8. Now here in the top right quadrant here is how we actually imagine a covalent bond forming. Two hydrogen atoms with their nuclei and their electron cloud. As they approach each other, the positive nucleus of the first atom starts attracting the electron cloud of the second, and vice versa. And as they get closer and closer together, the electron clouds actually start to overlap. Remember, these electron clouds are just electron probabilities. So when we talk about this atom and this atom, the electron from atom 2 and the electron from atom 1 aren't actually permanently stuck there. They're moving around within that electron cloud. But the probability states that they're going to spend a majority of their time right here in the center area. Imagine like you just got a new boyfriend or girlfriend. Yes, you're not going to be literally attached at the hip, but there's a high probability if I'm looking for you, I know where to look. Probably hanging out with them. That's where you're going to be. It's not, you don't belong to them. You're not permanently there, but the high probability is they're going to be together in that center region, shared. And this is what actually the covalent bond would look like. It's this overlap of electron clouds where there's a high probability of the electrons of both atoms being found in the region between that. Now, to represent these Lewis structures, what we call Lewis structures. Lewis structure is a representation showing the various all valence electrons of various compounds. And we're going to distribute these valence electrons in either non-bonding lone pairs. So we're going to either draw these as dots between dots around the atom. Non-bonding means they are not associated with a bond. They're just floating around in an electron cloud. Lone pairs, we're saying they're paired up, but they're by themselves. They're paired up in like an s orbital, not being used. Or they're in a covalent bond. Depending on how you want to draw this, covalent bonds can be just a straight line. It can be two dots between the atoms, either vertically or horizontally. But either way, we have some sort of indication that the electrons are being shared. These covalent bonds could be represented as a 2-electron single bond, a 4-electron double bond, 4-electron double bond, or 6-electron triple bond. Each bond shares 2 electrons apiece. But the important thing is that all S and P electrons must be accounted for. This is why we have some of the things. HCl, Cl has 7 valence electrons. H has 1. We should see 8 electrons. Looking at the structure there, we see 2 in the bond, and then 6 as lone pairs around the chlorine. Oxygen should have 6 electrons. 2 oxygens means 12. We have 8 in lone pairs, and 4 as 2 bonds. So that brings it up to 12. What you notice, if you count the bonds, that's 4 electrons plus 4 from the lone pair. Each oxygen has 8. Nitrogen. Each nitrogen has 5, meaning 10 electrons. 6 in the bonds, 4 at lone pairs. Each nitrogen has 8. This is why nitrogen is so stable. It's going to have a triple bond. It's why nitrogen is relatively unreactive, because of this triple bond, as we'll see later. Shoot, went too far. Now, the Lewis structure, all valence electrons should be accounted for. Octet should be followed whenever possible. Sorry. due to this octet rule, there's a strong inverse correlation between the number of valence electrons and the number of bonds. Oxygen, because it has 6 valence electrons and it wants to get an octet, it needs 2 bonds. It needs to share 2 electrons to get that octet. What did we see in the last slide? 2 bonds. Nitrogen with 5 would want to make 3 bonds, that triple bond. Carbon with 4 needs 4, will make 4. Fluorine with 7 only needs to make 1 bond. Chlorine with 7 only needs to make 1 bond. Bromine, iodine with 7 only need to make 1 bond. This is the reason for our diatomic gases. Fluorine, chlorine, bromine, iodine are all diatomic because it's more stable for them to make 1 single bond with themselves. Some of these structures we see on the right are how these elements exist in nature. Phosphorus isn't just P, it's actually P4 in nature. It's going to make this weird triangular structure where phosphorus, remember, below nitrogen, likes to make 3 bonds. You see each phosphorus in the corner is making 3 bonds with 3 other phosphoruses. Sulfur doesn't just exist as S, it actually exists as S8 because each sulfur is trying to make 2 bonds. And we need 8 of those guys in order to make a full ring with a stable, where they're equally distant and it doesn't put any strain. But sulfur actually exists as S8 in nature. But all of these sulfurs have an octet. Now, how do we draw the little structures? You can play around and try things out and maybe you'll get lucky. And you can, if you're kind of artsy and you're good at guessing and trying different possibilities, you like to puzzle it out, you don't need to follow these rules. You just need to try it until you can get it. But, and here's the thing, if you are struggling, these rules are something great to fall back on. If you follow these rules, it should lead you correct. There's often more than one right answer. If you can argue for this is a valid Lewis structure, you can usually get points. This test, the test for this, which is test 3, I don't know how we're going to do drawing these structures. So we'll have to figure out how to do those, submit those separately or something like that. I'm not sure how we're going to do that online. So drawing the Lewis structures, breaking down to these 7 steps. The first 5 or 6 are probably the most important. 1, sum all the valence electrons. You want to know how many electrons you have to deal with, how many electrons you have to work with. 2, select the center atom and put all the other elements around it. The center atom, if you have a chemical formula, it's typically the first atom in the chemical formula. Except hydrogen. Hydrogen is rarely the center atom because hydrogen can only make 1 bond. So it's typically the first atom and it can make the most bonds. We want that guy in the center because we want most things branching off of it. Place 2 electrons in a single bond around every atom coming off the center atom. So use electrons to make a bunch of bonds. Now, all that's pretty straightforward. Those first 3 steps are pretty straightforward. Now, here's the tricky part. Step 4, add remaining electrons to all the outer atoms until everything has an octet. So add remaining electrons to the outer atoms until everything has an octet. 5, if, and this is a big if, usually this step can be skipped because there's no electrons left. But if there is any electrons left, we place any remaining electrons around the central atom. Then finally, this is the tricky one. Check the octet for all atoms. If there is an if the center atom does not have an octet. Shift unpaired electrons, the lone pairs, into double bonds. Shift them. So basically, I'm going to grab 2 electrons around a satellite and pull them down into a double bond. I'm going to pull them down into a double bond to double up, because the satellite doesn't lose those electrons when it shares them. It still gets to keep them. It just now the center atom gets to count them as well. And we're going to do that until there's an octet on the center atom. And then finally, step can sometimes be skipped, but verify all electrons are accounted for and octet rule is obeyed wherever possible. Now, the best way to do this is to see this in practice. And so that's what we're going to do. We have CO2, NH3, HCN, BH3. And so we're going to try that. Start with carbon dioxide. Carbon dioxide. When we look at the valence electrons, we're going to look at what group they are. CO2. Let's see if I might have a better marker in here. Yeah, that might be a little bit. CO2. Yeah. Carbon is in group 14 or 4A, so it's going to have 4 electrons. Oxygen is in group 16 or 6A. It's going to be 6 electrons. 2 oxygens, so there's 2 6s. 12, we have 16 electrons. So that's our first step, 16 electrons. Carbon appears first in the compound. It can make the most bonds. We're going to put that in the center. C-O-O. There we go. And I really don't care. You could do it like this. C-O-O. That's still acceptable. We don't know any better right now. That's fine. Use 2 electrons each to make single bonds. That's 4 electrons. I'm now down to 12. Carbon has 4. Oxygen has 2 and 2. So I'm going to take 6 electrons and put them around 1 oxygen to give it octet. That's an octet. And another 6 electrons to put that around the second oxygen to give that an octet. Doing that over here as well. So here is, we can skip step 5 because I've used up all 16 electrons. 2, 4, 10, 16. So we have no more electrons. We can't put any electrons around the center atom. Now step 6. Here's the tricky step. It's a step it's going to take practice for. Move lone pairs down to make double and triple bonds to give the center atom an octet. So I'm going to start by moving 1 pair down to give carbon 6. So now this is still 1, 2, 3, 4, 5, 6, 7, 8 on this oxygen. Still 8 on this oxygen. I'm going to do the same over here. And now this is a valid Lewis structure. I've moved 1 lone pair off this oxygen, 1 lone pair off that oxygen. And we have CO2. We could have also done this. Move 1 lone pair off this guy, a second lone pair off this guy. This is a valid Lewis structure. Is it the best Lewis structure? No. But at this point, we do not know that. At this point, is this a valid Lewis structure? The answer is yes. This oxygen has 2, 4, 6, 8. This oxygen has 2, 4, 6, 8. This carbon has 2, 4, 6, 8. Everybody has an octet. Everybody is happy. That's an important thing. That octet is achieved for all atoms. Is this the best one? No. We'll learn why. This is a different structure. This will be what's called a resonance structure, but we will probably get to that on Monday. Working our way down. NH3.
Did you ever just put them all? Will that overdo the carbon?
What?
When you put double bonds, just 4.
4 double bonds?
No, carbon, and then 4 little bonds.
Oh, yeah, you could do that in certain cases, but there's not 4 atoms. There wasn't 4 atoms to make it to. So NH3. NH3. If NH3, let's work it out. N, group 15, or 5A, that's 5. And there's 3 hydrogens. 1, 2, 3. That puts it at 8 valence electrons. N comes first. It can make the most bonds. It's going to be in the center. So 1, that's step 2. Step 3, I use 6 electrons to make a single bond to everything. Now here we go. Step 4, we add electrons to the outer electrons to give either octets or doublets. Hydrogen is happy with its doublets. We don't add any electrons to the hydrogens. Step 5, we add the remaining electrons to the center atom. Step 6, we don't need no stinking step 6 because the center atom has an octet. Step 7, is everything valid? 2, 2, 2, 8. Everything has everything it needs. Ammonia has achieved its octet. That's NH3. That's ammonia. HCN. HCN, even though H appears first, H is never the center atom unless there's only 2 elements. So C is going to be our center atom, but 1 plus 4 plus 5. We have 10 electrons. C is our center atom. H, N. We're going to make single bonds. So that's going to use 4 electrons of my 10. This has a doublet. This has 4. This has 2. Step 4, we put electrons around the outer atoms to give them an octet or doublet. Nitrogen wants an octet, so I put 6 electrons around the nitrogen. That becomes an octet. I'm out of electrons. Once again, I shift. I have no more I can put on the center atom. But what I can do, shift pair 1 down, shift pair number 2 down. Now, this has doublet, octet, octet. We've achieved a Lewis structure. H, single bond C, triple bond N, lone pair on the nitrogen. One more structure, BH3. BH3. Boron, group 13 or 3A, 3 valence electrons, 3 hydrogens. So we have 6 electrons. B can make the most bonds, put in the center. H, H, H. Single bond, single bond, single bond. That's all 6. What do we know? Step 4, we have no electrons. Step 5, we have no electrons. Step 6, we have no electrons we can shift.
Wow.
Boron,
It's boring.
well, it's boned. Boron is stuck with below an octet.
Oh,
There's nothing that can be done. We can't do anything with it. It is perpetually without an octet, unless there's certain special cases it can make it. But it's hard to get an octet because of this only having 3 electrons. So there'll be some certain cases where an octet is impossible to achieve. We're just shy of electrons. There's too few electrons. So sometimes that will happen. And there's not much we can do about it. Boron is one of those pretty common cases. But as I said, this is something you need to see, you need to practice. With practice comes familiarity. Now, we will also look at some organic compounds. Any of you who are going into pre-med will have to see this. Any of you in nursing will have to see this to some extent if you take the second semester of nursing. Organic compounds contain mostly carbon and hydrogen. They have occasionally some other elements like oxygens and halogens, nitrogens, but it's going to be made up of fragments of what we know. But it's going to be a lot of chains. These chains, each chain will have a central atom. So there's not just one central atom, but typically, more than one central atom. And in order to determine connectivity, we're going to use the formula as a hint. If you have to take organic chemistry, the name will tell you later, but we're not there to naming these guys. So we're going to use the formula for a hint. We can also use to a lesser extent for complex inorganic compounds. So the examples I give: CH3, CH2, NH2. That is ethylamine. Ethylamine is what it would be called in organic, but CH3, CH2, NH2. CH3, let's write that. CH3, CH2, NH2. 4 plus 3 plus 4 plus 2 plus 5 plus 2. 7, 6, 7, 20 electrons. Breaking it down: CH3, CH2, NH2. CH3, CH2, NH2. Breaking it together, I'm going to connect these chains. CH3 connected to a CH2 connected to an NH2. Now, how many electrons have I used? I have made 2, 4, 6, 8, 10, 12, 16, 18, what? 2, 4, 6, 8, 10, 12, 16, 18. Sorry, 18 electrons. I've used 18 of my 20 electrons. That means I have 2 electrons left to place. Who needs them? 2, 4, 6, 8. That carbon's good. 2, 4, 6, 8. That carbon's good. 2, 4, 6. It's on the nitrogen. And now it has 8. That is ethylamine. We're using that as a hint. CH3, COOH. This is acetic acid, or CH3CO2H. So what that is, CH3 COOH. CH3 COOH. How many electrons? 7, 4, 6, 7, 14, 20, 24 electrons. We have how many accounted for? 2, 4, 6, 8, 10, 12, 14. We've accounted for 14 electrons. So that means there's 10 left to place. I'm going to put them around the outer atoms, so I'm going to put around oxygens. That's 6, 7, 8, 9, 10. So I've used all 10. Now what do we find? This guy has 8. This guy has 8. This guy has 8. This guy has 6. So what are we going to want to do? Pull one lone pair down. Double bond. So CH3COOH. There's going to be CH3, C double bond O, OH. That guy would be acetic acid or let's see, ethanoic acid, named properly in organic. Looking at the last two, CH3O, CH2, methylchloromethyl ether, something like that, or methoxychloromethyl, but CH3, O, CH2, Cl, breaking it down into each individual chain. 7, 6, 6, 7, 14, 20, 26 electrons. Carbon, hydrogen, hydrogen, hydrogen. O, carbon, hydrogen, hydrogen. Cl. How many have we used? 2, 4, 6, 8, 10, 12, 14, 16. Use 16. So that means there's 10 left. That guy has 8. That guy has 8. So we're going to put 2 on here to give that oxygenate. 6 on here to give the chlorinate. In fact, many of these organic compounds are going to be rather simple once you learn how to put the chains together. They're not going to be nearly as complex as some of the other structures we'll draw. It'll be pretty much put the chain together, add a couple lone pairs. But HSCN, that one is a little tricky. That is a complex inorganic. Hydrogen thiocyanide or thiocyanate. HSCN 1, 6, 4, 5, 10. Going to be 16 electrons. HSCN 2, 4, 6. We have 10 electrons left. We're going to want to put 2 on the sulfur, 3 on the nitrogen, 3 lone pairs on the nitrogen, and then we have to use all 10 electrons. And then we're going to start shifting to give carbon an octet. We can do this. Shift 2 pairs from nitrogen to do this. You could also do this. Shift 2 pairs from the sulfur. That's another valid Lewis structure. You could also shift 1 pair from the sulfur and 1 pair from the nitrogen. Both of these structures achieve an octet for all atoms involved. There is often more than one right answer. Sometimes one answer will be better than the others, but if I just ask for a valid structure, anything that achieves an octet on all the answers, follows those rules, is going to be valid. So that is where we're going to stop. That is where we're going to stop. We're not going to go any further because this is as far as we got in the Tuesday, Thursday class. So with that in mind, finish up the homework for chapter 4 and 5 if you haven't already. Finish up any labs you got, send them in. And I'll send out the test Monday at the earliest, Wednesday at the latest, and it won't be due till next Sunday. So thank you for your time, and I'll see you on Monday.